is one of a handful that have stable water isotope tracers embedded within them, and they were originally put in there for mainly for paleo climate applications. But there's the potential, perhaps, to use these as an to use these new measurements as an observational constraint on the underlying on the isotopic physics and its performance that way, but also maybe on the underlying cloud physics. That's eventually where we're headed. But in order to do that, certain properties of the satellite need to be taken into account beforehand. And so that's what I'll focus on today, is a retrieval parameterized simulator or parameterization that we put in the model, not, I guess, unlike the ISCIT simulator, that allows us eventually to make meaningful comparisons to the observations. So that's what I'll focus on. So it's largely methodological in going over what we have, the issues that come up in doing that, and what we've how we've addressed those. I'll just start off with a few definitions. If this isn't, these aren't everyday quantities. So water comes in a few different varieties. Regular water, H2O, is by far the most abundant, but there are two isotopologues, we'll just call them isotopes, that exist in small but measurable quantities. And the rare heavy isotopes, they evaporate less readily but condense more easily. And so over the lifetime of an air mass, for example, all of the that fractionation, we call it, will print upon the moisture an isotopic signature, which can be different from the overall moisture amount. And we'll always talk in terms of the isotopic ratio, which will either be just the raw ratio between these retrievals are for the deuterium, which can be retrieved in the infrared. And we'll talk about the ratio of the deuterium to the H2O. That'll be when we're talking about what I'll describe as the retrieval operator. When we talk about the actual quantities, it'll be in delta D units, which is it's this ratio, but relative to an ocean water standard. And so, just to orient ourselves, I'll start here. Here are annual means over the tropics.
Sorry, so the ocean water standard, though, is going to vary with temperature and salinity, right?
Very little. Only by, so the scale that we're by between 5 and 10 per mil relative to this range here. And actually so much smaller than what you see in rainfall or the water vapor. So here are these are from tests over the tropics, and all of this analysis will focus on the tropics over this period, over the lower free troposphere where the retrieval is most sensitive. What I want to illustrate here is that there's maybe some correspondence between the two, but there's no entirely clear relationship between the moisture amount and its isotopic composition. One thing I'll point out now is that the H2O, the specific humidity from the water retrieval, is very heavily constrained by reanalysis, unlike the delta D. See that right toward the end. Yeah.
So when I hear Aura, I think it's limb sounder. This doesn't look like
no,
limb sounder.
it's nadir. There are limb retrievals. I don't think they work very well. I've never seen any analysis of limb measurements, but
for what it's worth, I'm glad it isn't 8 limb sounder.
Well, in the lower troposphere, yeah, but there are other come back to it. So I'd argue that a model must be able to reproduce both the moisture amount and its isotopic composition. And I think that's been a useful idea in UTLS studies for strat-tropics change. For example, in identifying diffusive versus convective overshoot into the stratosphere, but which hasn't been applied in the troposphere, mainly due to the absence of measurements. And what we want to get at is that the discrepancies in the model versus satellite isotopic composition are more likely due to errors, we'll call them, in the underlying cloud physics than to the isotopic physics, for the simple reason that the isotopic physics are much simpler. And so we can use this potentially as an observational constraint when we're doing, say, perturbed physics tests to the cloud physics. And over the last, and it's only over the last 5 years or so that there have been enough data to evaluate the model this way. And so I'll talk about tests, but there are other SKIA. There are total column retrievals, isotopic retrievals, but that are mainly work over land, and then ACE, which is a limb sounder. There have been a few different versions, retrievals in the UT LS.
So are there, I thought there were complexities in that. I mean, if you're laying down layers of ice, the ice isn't going to be well mixed, right? It isn't. I mean,
there are, but to describe the isotopic composition, it's the hard part is to get the ice itself right.
I agree that cloud physics is a very hard problem, but I mean the layering. I mean, it's not that there aren't problems.
It's not that
they're
no.
lesser problems.
And especially for mixed based processes, they're certainly not perfect. But I think they're easier to constrain with lab measurements, for example. If you had, say, perfect.
I just a quick question about Skimaki.
Yeah. I don't know much about it, but
well, that's okay. I just want to know what you do know. And when you say it's mainly over land, is that with respect to water in particular? Do you know, or is it?
I don't know. It's,
I mean, you could.
There are some products from Skiamaki that they are overseas.
But not water.
Many. I have no
Like
idea.
trace
about
gas
water.
retrievals.
Trace gas.
Yeah, exactly.
Yeah.
Oh, they're mainly overseas.
Mainly, I don't know about that.
Oh, yeah.
But they are
Okay.
definitely overseas.
If you look at the retrieval quality field from SKIA, it's much more sparse over the ocean. I'm not sure why, or if that's generally the case. Like in all these cases, the isotopic retrievals weren't the primary motivation in mind in designing the instrument or the retrieval. They were mainly for tropospheric pollution, ozone and carbon monoxide. But they're at a high enough spectral resolution to apparently pick up the lines. And that's sort of the extent of my knowledge.
I love calling it skiers because it's such a terrible acronym.
Yeah.
No, it's not. It's a Greek word.
Skimaki?
It's a combination of two Greek words. John Barrows always says that means presentation.
Well, shoot me now.
Well, this is the last time I'll talk about it, so we
Yeah.
don't need to.
At least with a Greek in the room.
So I'll start sort of with the, so here's that same isotopic field, and here's the difference between the raw model fields and the observations. Same range. And you can see right away that the model delta D is significantly lower or depleted than the test measurements, especially over land. And so we could start to try and understand why that's the case. However, but we can't do that right away, in that certain features of the retrieval must be taken into account before we do any quantitative comparison, namely that model profiles that would be poorly retrieved by the instrument need to be excluded from any analysis, as is done in any observational analysis. And then for those, and then an instrument operator must be applied to the remaining high quality retrievals, which takes into account any potential biases in the retrieval having to do with how the retrieval algorithm works, which I'll talk a little goal in doing so is to produce what we call an instrument equivalent model field, and trying to estimate what would the instrument retrieve if it were flying inside the model. And so what I'll get into and is how we make that comparison, and so we'll talk a bit about this, the HDO operator, the standard approach in applying the operator, which originates, I guess, in studies involving models involving fully prescribed CTM studies involving prescribed meteorology, and why this might not work in some cases, at least for what we're interested in. And we'll describe the new approach that we've built into the model, and then compare what both do to those raw model fields that I had shown before, and then a bit of comparison at the end with the actual observations. But I'm mainly going to talk about how we make this comparison, unless I'm trying to diagnose why these biases exist, which is Aura's on the A train with a repeat cycle of 16 days. So that, first of all, needs to be taken into account, the Aura path. The HDL retrieval is based on emission spectra in the mid-infrared. And the retrieve profiles, the retrieval is based on optimal estimations, so they represent, the retrieve profiles represent are an adjustment from prior constraints for the water and HDO amounts, and this involves use of a full forward radiative transfer model, where the retrieve profile is adjusted iteratively using nonlinear optimization to minimize the difference between the spectra predicted by the forward model and that measured, right? And so a product of that of the retrieval is the sensitivity of the retrieve profile at any level to the isotopic composition throughout the rest of the column. And so we use that in computing the model isotopic ratio that we want to eventually compare to the measurements. And this, so all I want to point out here is that that new ratio has contributions from that prior assumption, which is, you can think of as the initial guess. So the ratio and the amounts, and then the raw model profiles, and then these averaging kernels, which are from the radiative transfer model and reflect the sensitivity of the retrieve to the actual profile. And the trick in doing this is first of all in doing the retrieval quality filtering, and then in picking what averaging kernel to use, because they'll vary with in the satellite data, they'll vary with each retrieval, and that mainly reflects the underlying meteorological conditions, for example, the presence of thick clouds. Here's an example. Here are example average HDO averaging kernel rows from a single retrieval. TESS is general for water, and HDO is sensitive, mainly sensitive in the lower free troposphere, which is where all of the analysis will be over. And you can see that, so for the retrieve profile, say at 619 millibars, for this line here, is, as you might expect, most sensitive to the isotopic composition over that range, and that those two, and that where it is most sensitive, and that's where it tends to peak. And so this will be the height at which, over this range here, the height at which the retrieval sensitivity peaks will be our main characteristic that we use in describing the averaging kernels. This whole issue is going to be about what averaging kernels do we pick? And so this is the main way that we'll characterize them. And I just wanted to point out that it's in that expression before, the second, the water and HDO are jointly retrieved in tests. So if you've done this stuff before for ozone or for other species, for example, the operator is simpler because of that. And then when they're jointly retrieved, you need to take into account the covariation between the two. And for example, the sensitivity of the HDO to the H2O amount. But those tend to, but in that expression before, these two, you can see that they're about the same and they'll tend to cancel each other out. And then for the sensitivity of the water to the HDO is much smaller if you look at the scale. So this is the important one, and is the big focus. So the standard way of applying the operator is to sample the model fields at individual satellite points. Just skip over the retrievals that are identified that are flagged as poor quality. And then for those remaining, take the averaging kernels from the individual measurements. And for this one, for example, this shows the orbital path and just showing the high quality retrievals only. And for the high quality retrievals, applying the satellite observed, the averaging kernels from the measurement points. And that whole approach originates from satellite validation studies. We're comparing the retrievals to in situ measurements. And just to reinforce that, I've shown an example for ozone here, where the assumption is that there's agreement between what the satellite sees so it started with observational studies and then has been applied in the chemical transport model studies, where all of the meteorology is prescribed. There's maybe it's reasonable to assume that, say, the cloud fields between the satellite and the reanalysis would agree. Although I've never seen that fully evaluated, and that's really what we're trying to get at. But you can maybe understand that it's a fair assumption. But if they don't, which would be the case for a fully free-running atmosphere, there's no expectation that the cloud fields, for example, would agree between the satellite and the model. And so by just using collocation like that, you're very likely to be just throwing out the wrong model profiles and using the wrong averaging kernels, which defeats the purpose of applying the operator in the first place. So we've tried to develop an approach that predicts in a very empirical or statistical way the retrieval quality and averaging kernel structure from the actual model conditions. So looking at the cloud cover in the model and saying, well, what would tend to be the associated averaging kernel for those conditions, rather than relying on the collocated measurements. So I very much see this as it's a two-step process in filtering out the poor retrievals and then choosing the averaging kernel. Here's the retrieval quality. These are from the test observations. Here's the retrieval quality over that same period. So in each cell, the proportion of retrievals that were classified as high quality, and you can see there's over the ocean, for example, there's decrease over the rain bands here a bit, but also over the colder anticyclonic regions off the coast, and then over land where it's hot and dry. But there's no apparently simple rule that you could use to classify those. And then for this height of peak sensitivity, and this is based only on the high quality retrievals because you've tossed all the bad stuff. That height of peak, what this shows is that for the for the remaining profiles, in that the over the lower free troposphere, that where it's over the wet regions, those retrievals are more sensitive to the isotopic composition higher up, compared to, for example, over the subtropical anticyclones where it's drier in the free troposphere. And here, that peak sensitivity will be drawn closer to the surface where there will be abundant moisture, right? So in the absence, so here, in the absence of any free tropospheric moisture, the moisture in the boundary layer, the isotopic composition of the boundary layer will exert a stronger influence. And so what we want to do, even before comparing looking at the effects of the operator on the raw model fields, and certainly before comparing the delta D between the two, we want to evaluate see how well we can predict these two based on the model conditions. So the first is to understand the observational controls on those two things. And so these are the pattern correlations between those two fields, the retrieval quality and then that pressure of the peak HDO sensitivity, the pattern correlations with those and a series of different underlying met fields that could potentially be important. And then so over the ocean, for example, is the cloud fraction, which is defined as the proportion of cells with cloud optical depth itself doesn't seem to be a strong control, I think because of how it's distributed. Cloud fraction, however, which is defined as the number of retrievals with cloud optical depth less than 0.3, which is a standard ISKIP definition, is a stronger control. So just as we would expect, the retrieval quality goes down with increasing cloud cover.
Oh wait, only over the ocean? It's the opposite sign over land?
Yeah, and I think that's because of the covariation between the cloud cover and the moisture amount. And if it's too dry, the retrieval won't work. There's just not enough, especially maybe for H2O it will, but for the deuterium, which is the concentrations are much smaller, it won't. Yeah, so overland, and which I think is that's reflected there in the surface temperature is seems to be the strongest control in retrieval quality overland. And then for that pressure and peak sensitivity, the strongest relationship is with the water amount, which we're using the precipitable water and separating it into boundary layer and free atmospheric water, and it's that which tends to be the strongest control. This is important, but it doesn't vary as much. It varies very little over the ocean. It's always moist in the boundary layer, but that's not the case higher up. And then over land, surface temperature also seems to be important, but those will co-vary so strongly with the moisture. And I'll just say that I tried coming up with trying to make this more sophisticated with multiple regression models, and it didn't.
Can you say a little, what goes into retrieval quality? We can guess what goes into the other one's intuitive. What goes into retrieval quality?
Yeah, for the satellite beam, for the product, satellite product.
Like what determines it?
Yeah.
There's a sensitivity. One is if the optimization just doesn't converge, right? And then there's also a sensitivity threshold. If you think about those averaging kernels and where it peaks, if that's too low, then it means the retrieval is relaxing more toward that prior. The satellite's not providing as much information. And what influences that is mainly, in the ocean at least, is the presence of thick precipitating clouds for the IR retrievals.
So your problem is getting signal. You don't have a saturation problem. It's just
Well, I think that could be the case over land for those really hot if you saw the retrieval quality over the Sahara was low, I think because of that, which I think is actually to show that, which which is, so these, for each of those fields that were identified as strongest, here are the scatter plot relationships. So retrieval quality goes down with increasing clouds, and then it does, but more weakly over land with the surface temperature, and it's really driven by those points, the really hot conditions where I think it's exaggerated. So these, so here are the same plots, but for that height of peak sensitivity. So for this, or the retrieval quality, I'm going to adopt this as one way of evaluating how well we're doing the retrieval quality filtering and the averaging kernel selection, in that we don't exactly, we'll see a bunch of predicted fields in a minute, and they shouldn't necessarily match those from the satellite, right? Because if the model has, which it does, has a lot more cloud than the observations, then then those instrument equivalent fields should have lower overall retrieval quality. Both are comparing the actual fields. I mean, they're good as a sort of a sanity check, but I think this is the more this is the better way of evaluating it. So that's all based on the observations. Now getting into the model part, we're working with the standard version of the model with the isotopic tracers over the same observational period, with some spin up before that, prescribed SSTs, and then in this case we are nudging the winds, so it's sort of so it's not fully prescribed meteorology, but I want to do it, it's sort of a test bed situation where we do actually want to see how close we can get to the observed fields. I'll talk a little bit about free-running simulations later on and how it performs there. And all of this stuff has been put inside the model rather than applying it just as a sort of a technical note. That's where it all exists now. And we put it inside the model rather than apply it after the fact, so that we can, just to reduce the amount of data model output that we need to generate. Particularly because we want to do sort of small or medium-sized ensemble runs where producing daily, or if we're only interested in sort of the mean state or the monthly variability, doing it offline, you have to produce daily or synoptic output to apply the TESS operator, which creates a prohibitively large amount of data for any sizable number of runs. So it's all inside. And what the starting, so like I said before, it's very much an empirical approach, in that we made a bunch of big lookup tables from the observations, based on the meteorological quantities, all that are part of the satellite data, that would influence the retrieval quality or the averaging kernel structure. And so we take all the data and sort it according to different combinations of these variables, and then for each, so within each categorization, for each bin within a categorization, look at the mean retrieval quality, and then the mean averaging kernels and H2O priors, and then look those up in applying the operator to the model. So at each time step and location along the orbital path, sample those categorical fields in the model, look up that category from the TESS observations, which have all been pre-computed, and then include that model profile with probability equal to the retrieval quality, right? So if for a given set of met conditions, if there were 20%, if 20% of those retrievals were of high quality, then that profile would be included with 20% probability. And if it is, then take the associated averaging kernels from that category and use those in applying the averaging kernel, rather than what the satellite might have sampled at that point, but which might not be suitable for the model conditions. And this is sort of a cheap alternative to running the full retrieval algorithm inside the model, which is just possible, but is there are just technical reasons why that's difficult, and it could be more computationally, too computationally expensive. So before applying this, I wanted to get a sense of how. So we took all those variables and looked at and split them up in less and more complex ways, and these names sort of reflect what's in there, and these numbers just tell you how many bins there are within each of those. And you want to know how, for the retrieval quality, how much does the retrieval quality vary between each of those categories, and the overall retrieval quality is about 65%. So if they're all 65%, then you're not separating good from bad very well. And so this is the mean difference for each bin within a categorization and the overall mean. And that you get most of your separation just based on the clouds. Some help from the temperature, but those two you can get most of it using those two, which we saw in the which makes sense given the relationships that we saw before. Precipitable water, which we'll see is really important for the averaging kernel structure, doesn't separate the good from bad retrievals very well. And then we also want to determine how well the averaging kernels are separated. And so each of these are under clear sky conditions. This is that averaging kernel row at 619 millibars for decreasing amounts of precipitable water in the free troposphere. The black profile shows the overall mean for reference, and these are 1 sigma error bars around them. And then the gray profile shows that averaging kernel row for those decreasing free tropospheric moisture amounts. So as there's less moisture higher up, the retrieval becomes more sensitive to that, to the isotopic composition closer to the surface. So that's the kind of separation that we're trying to make. And so to quantify that separation, looked at the total. It's like the within group sum of squares squared error, basically the total error bar width. You want to minimize that total error bar width across all of the averaging kernels. And so you can see that you get, taking into account the complexity of that categorization, you get most of your separation just from precipitable water on its own, using only 9 categories, because we've separated separating boundary layer and free tropospheric moisture, compared, for example, to using these are the fine iskit categories for the clouds, so which give you very relatively little, and then there's still a decrease as it gets more complicated, although with diminishing returns as you get more complicated. And so based on that, we chose a few select cases, or I'll show a few select cases which show the differences between when you're trying to predict that from categorically rather than using collocation. Okay, so here's the observed retrieval quality, and here is the predicted retrieval quality from the model conditions using that lookup table for more complicated categorization. So this is clouds only, so using cloud optical depth and the cloud top pressure. Precipitable water only. I tried sort of a minimal categorization using all those variables that were most important. So land ocean separation, cloud optical depth, temperature, and then surface temperature and free tropospheric moisture. And then this is sort of the full shot with everything. And these two, so you see most of your structure from just in retrieval quality based just on the clouds alone, and then does but becoming a little more complicated when you get more complex. And I just wanted to point out that here, for precipitable water only, it doesn't look entirely different, and in the mean at least, it's more similar. But I think again, I think the better way to evaluate performance is to look at the relationship between, and this is sort of a minimum requirement, is to look at the relationship between the cloud field and the retrieval quality. And so the black dashed lines here show the regression lines from the observations, which we're trying to match the lines, not necessarily where the scatter is, because that can change depending on the model conditions. But I think that relationship should be similar. So, and that is, I think, the case for the operators involving clouds, but not for the. You see that here, how the precipitable water-based categorization doesn't work. Over land, it's harder, but you do get better performance as the categorizations involve in surface temperature. Here is the height of peak sensitivity in the lower free troposphere from the observations, and then for the more complicated categorizations, you get very little using the clouds alone, and it looks, I guess, more realistic when it's based on precipitable water alone. It's smoother because you're filtering, because you're not involving clouds. You're excluding fewer observations, so the field tends to be smoother, and you're including you have more sensitivity higher in the free troposphere because you're not excluding those precipitating clouds, and then these two look the same. And you can see that they start to look more realistic, and that's also the case when you look at the relationships between that peak height and the underlying drivers. Over land, again, it's more difficult, although they're more realistic when you for the more complicated categorization. Okay, so before, in theory, we could evaluate the performance just based on how well we think those are being chosen, but we want to start to get a sense of what effect all of this has on the model field. So this is the raw model field that I'd shown before, which I said was not suitable for direct comparison. And this is the field resulting from applying the collocated approach, right? Which we think should perform okay because we've nudged the meteorology to observations. And then these show the resulting change from the categorical approach. So we sort of want to get the same as this, but taking into account any differences in the modeled meteorology. And so these look fairly similar, especially these two. What I thought was most interesting, and what actually led to going back to looking at that height of peak sensitivity and using that as a diagnostic, was this decrease here over the dry subtropics, over the ocean. And what's going on here is that all of these or more of these are classified as clear sky, and you're not getting, well, I should just say before that the change, what's mainly going on here is a reversion or a relaxation towards the prior constraint, which for the HDO is about 150 per mil. And so values that are lower than that in the model, where the sensitivity can be lower, will relax more toward that prior, which is why we see the increase here, and then where the model's higher, we tend to see a decrease. That decrease is too strong here because when you just using clouds only, anything that's classified as clear sky will just tend to have that smooth, that averaging kernel peaking in the free troposphere rather than the one with most sensitivity, with greater sensitivity toward the surface. And so this, based on clouds only, you miss that. But that overall, but they all kind of look the same, because any averaging kernel that's included, it'll always have that same shape peaking somewhere in the lower troposphere.
Robert, from that top figure, can we turn around and then assume that the data that the satellite is actually giving us is usually overestimated?
The retrieve delta D. Well, I'm taking that as the truth. Right?
Sure.
I haven't compared. We're not comparing that yet. We'll get there.
I don't mean a comparison.
Yeah, biased, right?
Yeah.
And that's what we're trying to. There are biases in the satellite retrievals because of the for one reason, because of the influence of the prior that need to be taken account into any comparison against the model. Here are two quick sensitivity tests. One is the effect. This doesn't have orbital sampling. I just wanted to see if it had an effect, and the fields are smoother, but other than that, there isn't a big difference. Although that's over 4 years, so that will not likely be the case over shorter time scales, which is part of what we're interested in. Looking at comparing MJO, the isotopic signature of the MJO, for example. And I've talked mostly about choosing the averaging kernels, but we're also having to choose the H2O prior at each point because it will vary. And so this one just uses a single fixed H2O prior, and it doesn't have a big, doesn't make a big difference. Mainly if you go back to how the operator is expressed, the term involving that alone tends to be small because the averaging kernels cancel each other out. And I'll just say that it does not work as implemented. It does not work outside of the tropics. I won't get into it, but these show the zonal relationships, those correlations underlying the scatter plots when you extend it outside of the tropics, and what happens, you're just mixing, you're just over aggregating the averaging kernels and retrieval qualities over too big an area, and there could be other things going on, especially over land, that need to be taken into account. We're using finer bins, so we'll revisit that at some point. Okay, so here's, just to wrap up, here are some comparisons between the delta D fields from the satellites and the models. So here are the satellite measurements. Here's that initial difference between the raw model field and the satellite, which I said was inappropriate. And then here are the model differences for that collocation-based approach, and then the more predictive approach. And you can see that the bias goes down after applying the operator, which is nice, which wouldn't necessarily be the case. I think that could have gone either way. Whatever the case, these are the more appropriate fields for comparison against the observations. And you can see here that there's something different going on when you take into account all the features of the satellite retrieval. There's something different going on over land than over the ocean. So this which would have been less likely to see had that not been taken into account. These are all for the same nudged runs, by the way, and I'll just show that it seems to work okay for as far as the choosing the right retrieval quality filtering and averaging kernels. It seems to work fairly well for the free running simulations too. I'd shown these before. These are the relationships this is for a nudged run over land and ocean for that height of peak sensitivity. This is for a free running simulation. So in this case, it tended to be drier for whatever reason, I guess due to differences in the large scale circulation. But that relationship is fairly close to that from the nudged run. And so where we're going with this is to look at individual processes. I just wanted to see, for example, what is the isotopic signature. This is specific humidity in delta D over Indonesia, and there were 2 moderate El Nino events during the observed period. This is the black line is the test specific humidity. These are raw monthly values, no seasonality removed or anything, but you can see the drier conditions during the stronger 2006 El Nino and a bit during 2009. It's the gray line is from the Aura interim reanalysis, and the reason that the match is so close is because of the strong prior influence in the test H2O retrieval, as an aside. And then for a nudged run, you do see that drying out, but then worse performance for the free running simulation, as we would expect. I mean, I didn't really know what to expect as far as an El Nino response, just based on the atmosphere, based on the SSTs alone. And then we can start to look at what the isotopic response is during those events. And so during those drier conditions, you get an increase in the delta D, and which could be due to less intense convection, and which tends to recycle moisture and deplete and progressively lower the delta D composition. So we see that in the observations, and then maybe a bit of a response there in the model too, but not for a nudged run only. Anyways, that's where we can now start to look to and these are all for the models. These have the full operator applied. So we can, having done that, we can now start to make those comparisons. So so I'll just say that. So what we can do now, using the isotopic observations, is to make comparisons for arbitrary model configurations and not relying on any agreement at short time scales between the model and satellite, for which the sort of collocation-based approach might not work. But that to go outside of the tropics, we need to I think use even more categories, and maybe even split things up zonally. But the focus of the work we'll do next will very much be focused on the tropics.
Have you ever looked at like how well nudged like a reanalysis meteorology actually do better compared to free running? Or I mean, like maybe a direction might be it could be improved, but I wasn't quite sure. Like cloud, you know.
I haven't looked at clouds. I mean, the precip, it will be improved with the nudging.
Have you ever looked at it? Because for my case, when I do, it wasn't. I look at the certain location and it was pretty close.
Yeah,
so.
well, it's better. It's not great. Even when you nudge the large-scale circulation, you don't get as much improvement in the precipitation as you'd expect. And like I've just done the nudged runs here to simplify the situation. Eventually, we want to turn all of that off so we can have proper interaction between, say, the motion in the column and the large scale circulation. But I can show. I have that here after. I can show it to you. But as far as the rainfall goes, compared to trim, at least it's not as, the improvement isn't as big as you might expect.
It does well to improve the temporal variability, right?
Yeah.
it's able to
Yeah.
put the blobs of precip in the right place.
Yeah, like you can induce that, you can, like for that, I didn't put the figure there, but for that drying over Indonesia, you can induce a strong drying during the 2006 El Nino because you've moved the terminal end of the water circulation over. And so you can do that. But some of those, like the model I think is generally too wet. And that bias goes down a bit, but not, maybe not as much as you'd expect.
You talked about cloud physics. How are you going? I was hoping there's going to be some. You're going to show us how you're going to cleave problems with cloud
Yeah,
physics
we're
from
gonna solve
dynamics.
all of it. Yeah, well, like so the isotopes are really sensitive to, for example, to condensate reevaporation, right? Which is not a well-constrained free parameter in any, certainly in the GISS model, right? Or to reevaporation or entrainment strength. So it's not going to solve all your problems, but it'll be sort of an orthogonal observational constraint relative to moisture amount, just because the isotopic values are so sensitive to moisture recycling, for example. I've done tests where you turn a lot of that off. I've turned off the isotopic physics during, say, as the condensate falls and equilibrates with the moisture around it. And over the tropics, that's the key thing, rather than the initial fractionation during when it first condenses, which is sort of the classical Rayleigh distillation model of isotopic composition, which doesn't really, which doesn't apply in those situations. So you can see strong isotopic responses to changes in those parameters, for sure.
So in your methodology, you use cloud information and water vapor information to select retrieval quality and average kernel structure.
Yeah.
Do you have any sense which one is more important?
Average kernel structure, both, but given the choice between the two, it's the averaging kernel structure which produces most of that transformation. And I know of not for I haven't seen it for the isotopic, from test, for example, from the isotopic retrievals, but for some of the other pollutants, there aren't strong, when you include, say if you make it computed mean, there isn't a big difference when you exclude the poor quality retrievals from from all of them. So I'd expect that's the case here too, but I don't know for sure.
When you were showing us those regressions versus satellite, like cloud fraction, precipitate water, and then two you just called more complicated. And it seemed like the two more complicated ones were doing more for your land. And I was just wondering, in this second to last plot where you were showing like the biggest trouble being over land,
Yeah.
was that so I think even in the map view you could kind of just see it. I was just wondering,
Yeah.
was that true regardless of which of those last two more complicated ones you used?
Yeah. Or the sort of the minimal set they were both about the same. The full one was a little bit better. Land could be problematic because there are fewer measurements, because the bins, the mean averaging kernels and retrieval quality are less robust because there are fewer observations. And then there's just more going on there too. Like I haven't taken into account topography or land cover characteristics, which could be important, especially in going outside the tropics, right? Like that could be part of why the performance degrades so much. It's just because there is more land, and that's where most of the problems are.
And then, sorry, we just want to re-ask the question I asked earlier in a different way. So, are there any ground-based observations that get compared to the satellite?
A few, yeah, very, very few for the isotopic composition, and like there are no isotope songs.
And in those few, is the satellite biased high?
Camera.
Because that
Like we're talking
comparison-
very few, like you can count them on one hand, right?
Well, I mean, that comparison that you showed between the model's raw and the model's satellite view, what showed that in the model, the satellite's biased high. So,
Yeah, which could be the case, and that's what we're accounting for.
or it might be the case that your that your pre-processing is reliant on cloud fraction, which is off in the model, and so you're pre-processing in such a way to bias high. So I mean, I just
Sorry, say that again.
it would, for me, I think it would be nice to see that the high bias in the satellite, in the model flown satellite, was also
Yeah.
true of the actual satellite.
Do you mean like the big?
But then you need the unbiased satellite measurements, they don't exist.
Right, so that's why I was wondering about ground-based, right? I mean, see,
So you'd have to introduce a ground-based network into the model.
I don't, sorry, I wasn't thinking about the model at all. I'm just wondering if the satellite retrieval is just funded.
It's not well validated compared to ozone, for example, which I think really is like that's because there are far more measurements, and it'll still have its biases, but there's a lot more validation that goes on for ozone. There are aircraft campaigns and like ozone networks.
I thought they were balloons, but it just dozens or something.
It's all one-off campaigns, not necessarily. I only know of there have been validation campaigns over at in Hawaii and then one that's going on right now in the Andes. So at higher elevations where the retrieval is sensitive, you can actually we want to validate it. But I don't know of any aircraft campaigns. I don't know of any balloon measurements.
Crystal Face definitely
Yeah,
is doing this.
Yeah, that's true. And I think Gavin had looked at that before when he originally put the physics in there.
Actually, over land, the problem, one of the problems which we have is that we have to deal with separation of evaporation to transpiration and
Yes.
and evaporation from water, and isotopes are
They don't
separated
fractionate.
differently there, and we never sort of look at those portions because it's difficult actually to look because total evaporation is okay, and then we think that well that's okay, but how much goes to transpiration and how much it goes to wet evaporation, that's
So I think
what
that's
isotopes
what's
can
going on
show.
there, right? Like it could be different issues with continental convection, but I think it could be too low transpiration. So like the water doesn't fractionate through it fractionates through evaporation, but not transpiration. So it has so coming out of plants has a much different signature than evaporating off of the ocean or from soil moisture. And I think that's maybe what's being seen there, and that's
Yeah,
real.
I think we
which-
usually have
which cannot be-
transpiration which is too low.
Yeah,
Because that's
yeah.
the concept.
I have a question that's sort of going off into that sort of direction, from the vegetation side. So, for example, there's been estimates in let's say the Amazon basin, that an enormous amount of the precipitation here is literally recycled water.
Yeah.
I don't know enough about these in the community. So, if water is recycled, is it more and more fractionated?
Not over.
Is
It
it
wouldn't be over
additive?
the Amazon.
Meaning over the rainforests, where
Yeah.
you have huge transpiration, and
Yeah.
then the precipitation transpiration basically cycling in that area.
The intensive convection will deplete the moisture, but the strong transpiration will enrich it, right? So there are two competing effects there.
Yeah.
I mean, I don't know what one is going to win, but both will have a strong effect.
So would you expect, I mean, I'm really at
Yeah,
the
yeah.
edge of my understanding, but in places where there's less of this, I mean, quote, local or regional transpiration and recycling,
Yeah.
would you expect, even with a similarly dense forest, would you expect different isotopes?
Yes. Yeah.
So that's
Can you give us an nice hand wavy explanation why there's no fractionation and transpiration?
Yeah.
Yeah.
The plant acts as the reservoir, and so the rather than the soil or the water body, and so there's full throughput through the plant, and so there's no for a given amount of water coming up through the roots, through the stem and then the leaves, all of that goes out compared to a water body where only a small fraction of it is. So it's the amount of evaporation or transpiration relative to the initial reservoir, which for a plant is really small, and for a water body is, or even soil moisture.
So there's fractionation, but it's very small or something.
There is effectively there's no fractionation.
Yeah, basically transpiration, that's what the roots are taking from the
And
from
there's
the soil.
no
And they don't
phase
know-
change.
Yeah, and they don't know anything about the isotopes, they take everything. And then when you evaporate it from the leaves, I guess, well, if you
That's
start
where
the
the-
fluctuation, you will immediately accumulate in the leaves so much of excess of
Well, that's
anything
where
that you-
the phase
yeah.
change happens, but
Yeah.
And the leaf becomes the reservoir, but there's full throughput
Yeah.
of the water.
But there is very, very little water in the leaf itself, so you
Yeah.
basically
Yeah.
immediately compensate for any
Yeah.
fractionation.
I mean, because evaporation is just really net evaporation. You really they're going both ways all the
I don't
time.
know if it's that or
What do you mean net evaporation?
Well, I mean, it's not just molecules just going that way. Some are going down at the same time. So just because
Oh,
things are
well.
evaporating doesn't mean there aren't any water molecules that used to be in the vapor going into the.
yeah, it's a net.
Yeah.
So that's I don't understand.
Yeah,
that.
but you still have the main flux is going through the roots, so you get those isotopes from the roots. Even if you have equilibrium at the leaf, it just effectively just means that you have very high concentration or very low concentration of certain isotope because of fractionation. But still, the flux which you get from the roots have to go to the atmosphere because you cannot.
There's nowhere else to go.
Accumulate infinitely.
Hmm.
That makes sense to somebody.
Those damn trees.
It could be a little more complicated. I mean, they could accumulate something in the leaves, and if the leaf fall, you just drop that leaves. And, I don't know.
But in the tropics, they don't really drop them.
Oh, then you still drop them. It's just they grow.
Yeah, but not anywhere near on, they don't do them at even in the northern environments.
It's not annual. It's like every day that it drops. You can talk
No,
to
but I
Nancy
mean, the
about
leaf
that because-
turnover is not annually, and in fact, actually, just to throw some, in the northern, like for needles, which, I mean, they're replaced about every ballpark, every 7 years or so. Right? I mean, you have full replacement about every 7 years, so needles last a while,
Yeah.
and leaves in the tropics last a while.
So you're talking about the moisture in dead needles and the evaporation rather than the transpiration from the litter.
Well, yeah, technically, I guess that.
Yeah,
It looks like very small.
I doubt it's a large factor compared to.
Gone off on this vegetation thing.
No, but it's interesting because one potential use is to separate evaporation from transpiration. It's a potential. It's pretty different than what you can have the same moisture.
I mean, that
Yeah,
kind of
but also-
division is really easy. I mean, you really want sort of large scale, sort of big groups, and that's really easy.
But also, I guess water is used like as a building block for the biomass. So it would be that like
It doesn't add, it
certain
doesn't build up
isotopes
much.
can be stored there. I don't know.
No, that water is moving through, I mean, it's pretty much moving.
Yeah, but if tree is growing, it's not just carbon. It's also water. I guess is used as a building block.
The water content of wood is pretty low. But anyway, there is information about water contents of all those pieces of the plants, just in case you know. In that
What is
five
the water content? It takes some oxygen out of the air and makes
Pardon me?
sugar. It makes sugar.
Yes, I mean,
makes it cellulose.
Yes.
It's not water, but it's the hydrogen and oxygen. Half of it came from the water that's in the cellulose. We're talking about the
I'm not
atoms,
sure
not
where
the.
we're
We're talking
going.
about the atoms.
Oh, mhm.
Not the molecules, right?
Yes,
They're all-
maybe
You
that
never
our
comment
sugar
about the water
contains
content.
all the
It's not relevant, I throw it.
deuterium.
Okay, let's thanks to speaker.